All right, let's go through a few examples of concepts, some conceptual questions relating to moment of inertia. So as usual, please pause and try to determine what you think the answer is, and then watch the answer. So the correct answer here is B. We can show that mathematically, or if we remember that I is always related to mass and a distance squared, it's not necessarily equal to mr squared, but it's always related to a mass and distance squared. The distance being squared means the distance has a bigger role to play than the mass itself. So B is correct because the distance from the center is larger in B than in A. So even though they have different masses as well, the greater distance plays a role. Now, for those that like to see the math, to find the moment of inertia of an object that is like the rod plus these balls at the end, the I of a total object or system of objects connected together is simply the sum of the I's of the individual objects. So if I say the ball at the left end is ball 1, the ball at the right end is ball 2, now technically we would add I of the rod, but because the problem tells us to consider it to be massless, then it doesn't have a moment of inertia to account for. No mass means no moment of inertia. So ultimately, we just need to add I's of these little balls. Now these balls can be approximated as point masses. Wow, that looks awful. Let me try that again. Meaning the size of the balls individually is small compared to how far away they are from the rotation axis. So in system A, when we say I is mr squared for the ball, m is the mass of that ball, and then that r is how far that ball is from the rotation axis. Here the problem tells us that we're calculating or comparing the moment of inertia about the midpoint of the rod. So that's why I drew my rotation axis in the middle. So I total, ball 1 has a mass m. It is a distance of the total, 1/2 of the total r that they've drawn in the picture from the center. Ball 2, similarly, so we get 2 of these. When we square this, we get 1/4 r squared. So system A has a moment of inertia equal to 1/2 m being the mass of either ball times capital R, so the capital R that they've given us in the problem squared. System B, the same setup applies. Of course, we have half the mass, and now the distance from the rotation axis through the center is capital R. So I will take half the mass, and then I'm going to multiply that by r squared. Half the mass, multiply by r squared. So when we add these together, we get mr squared. I of system B is bigger because those masses are farther away. Again, the farther away the mass is, the larger the moment of inertia is. Ultimately, what that means, if you've ever lifted a dumbbell, for example, if we picked up either dumbbell in the center and then tried to turn it, so to twist it one way or the other, this one on the right, B, this one would be harder to rotate than the one on the left. So even though the one on the left has more mass, having that mass closer to the rotation axis helps to keep I smaller. Now, that's just a comparison. It doesn't mean dumbbell A will be easy to rotate per se. It's just easier when compared to dumbbell B. Go ahead and pause. Which answer do you think is correct? Correct answer here is B. So even though these are both the same mass, because all we've done is taken these extra discs, cord them out of the cylinder and place them in a different spot, the system overall has the same mass, but B now has more mass, a little bit more, farther from the center, where the rotation axis is. So again, the farther the mass is on average from the rotation axis, the larger I, the moment of inertia, is. The idea behind that also, have you ever at some point in your life tried walking on a balance beam or even a curb? Our instinct is, so we're walking along this balance beam, our instinct is to lift our arms. The reason why is if we were to start to fall, theoretically without catching ourselves, which we wouldn't do, we might start to fall, but we would catch ourselves. We would tend to rotate around where our feet are touching the beam or the curb. Lifting our arms increases our rotational inertia, our moment of inertia, which means now it's a little bit harder to make us rotate. So even though that's kind of a natural reaction, it's described in physics, which is kind of cool. All right, let's look at another problem. What do you think about this one? Well, B is going to be correct. Solid means on average the mass is closer to the rotation axis than hollow. If we look at the equations from the table, for a solid sphere, we have 2/5 mr squared. For a hollow sphere, we have 2/3 mr squared. 2/3 is bigger than 2/5. So even though they have the same mass and the same radius, the hollow sphere has a larger I simply because of that 2/3. But again, the 2/3 is bigger because on average the mass is farther. It's all on the outside edges of the shell. All right, one more conceptual question. All right, so a hoop, if I go back to the table, a hoop or a ring, mr squared, a disc, 1/2 mr squared, and a solid sphere, 2/5 mr squared. Moment of inertia, the smaller I, the easier it is to get it rotating, or to change its rotation, I should say. So just like I said before, a larger I makes it harder to change its rotation. A smaller I means easier to change its rotation. 2/5 is the smallest. So the net torque equals I alpha. The angular acceleration being inversely related to I, the solid sphere is going to have the largest angular acceleration. It's going to rotate the fastest. It's the easiest to get to start rotating and increase its rotation, so it will get to the bottom first. The disk would come in second place. The hoop would get to the bottom last. Now that doesn't mean they take huge different amounts in times, but they will always get to the bottom in this order.